For some sequences, kind of the standard limit tricks are good enough to tell if the sequence converges or not, but sometimes it's actually kind of hard to tell if the sequence converges. For certain sequences, there's a nice trick to know whether it converges or not, but the sequences involved have to have some special properties. So let's name some special properties. A sequence is called bounded below if there is a number so that a magic number m, so that your number is magic number m is less than every number in the sequence. So just for example, this sequence is bounded below by, say, 0. Right? Every term in this sequence is greater than 0. So this sequence is bounded below. Of course, so is the sequence 1 over n, right? For n from 1 to infinity. Right? This is also bounded below because this also never, because 1 over n is greater than or equal to 0 for every value of n. Right? So you can see lots of sequences are bounded below. A sequence is called bounded above if there's some fixed number that is greater than or equal to the sequence for every term in the sequence. And a sequence is called bounded if it's bounded above and below. Okay, fine. More properties that sequences can have. A sequence is called increasing, or really eventually increasing, if each term, a sub n plus 1, is greater than the term before it, a sub n. At least far enough along in the sequence, so for all n large enough. So what I'm saying here is, right, the first few, we can graph sequences by, right, putting our values of n on an n axis and then using heights to represent the value of the terms of the sequence. So what I mean by eventually increasing, or all n large enough, is that, right, our sequence might jump around a little bit at first, but from some point on, if it is always going upwards, then it is eventually increasing. A lot of what we'll do with sequences, what matters is what happens sort of eventually, and so the first few terms in the sequence often won't really matter whether it's well behaved or not, as long as it's well behaved eventually, and this is an example of that. Okay. A sequence, of course, is called eventually decreasing if each term is less than the term before it for n, all n large enough. And here's the key thing about all of these properties. And this is something that we aren't going to prove. I'll comment on it. But anyway, here's the fact. Any increasing sequence that is bounded above converges. And any decreasing sequence that is bounded below also converges. Now, one funny thing about this theorem is that it doesn't tell you what it converges to. It only tells you that it converges. Right? This should seem plausible because suppose that we have, say, a decreasing sequence that is bounded below. So say our lower bound is m. If our sequence is decreasing, right, that means it's always going down. Well, if it never goes below m, it has to cluster up against some ultimate value out here on the right. We don't know what that value is, right? It might not be m. It could be larger than m. Definitely can't be lower than m because we said m is a lower bound, so our sequence can't get down below m, so that can't happen. But it has to sort of run up against some value, right? And you can draw a similar picture to convince yourself that an increasing sequence that is bounded above also converges. The reason we aren't going to prove this is that this is essentially part of the definition of the real numbers, right? If we had a decreasing sequence bounded below like this, and there were no limit, that would mean that there's a hole in the real number line here, but a defining feature of the real number line is that it doesn't have any holes. So this is essentially the same as saying the real number line doesn't have any holes, which, yeah, it's the real number line. If it had a hole, you'd make up a new real number and stick it in the hole. In fact, that's how we come up with the real numbers, right? You look at all the rational numbers and then all the holes, you give them names as irrational numbers. Okay, so using this theorem, let's check if this sequence, x to the n over n, converges, and x can be any real number here, but it is fixed. Okay, so we have thought about this sequence before, but now that we're a little more sophisticated in our thinking about sequences, let's look at it again. So does this sequence converge, and if so, to what? Well, let's... actually, sorry. I want x to be positive. If it's 0, then of course the whole sequence is 0, but let's think about positive x. It's hard to tell whether this sequence is increasing or decreasing, right? If it is increasing or decreasing, and if we can come up with a bound, then right, we can use this theorem, but it's hard to tell if this is increasing or decreasing the way that it's written. But what we could do is realize that it actually is a recursive sequence. And it's a recursive sequence because if you have the nth term, right, remember the nth term looks like this, you could get the n plus first term by multiplying by x over n, right? So we can double check this just by taking our nth term, which is x to the n over n factorial. I made a mistake here. I should have a plus 1 right here. If we multiply our nth term by x over n plus 1, what we get is x to the n plus 1 over, and then n plus 1 times n factorial, that's n plus 1 factorial. Okay, so this sequence that we've written down actually is a convergent sequence, okay? Or I'm sorry, recursive sequence. That's what I meant to say. So our sequence is recursive. And having it be recursive is kind of nice because it can make it easier to tell if your sequence is increasing or decreasing. That's what I meant to say. So let's see, is this increasing or decreasing? Well, let's check. So n is eventually bigger than x, right? Because we're thinking about a limit as n goes to infinity. X is some finite fixed value, so eventually n is going to be bigger than x. So let's think about, and that means that n plus 1 is also going to be bigger than x, right? Eventually. Right, so remember, the word eventually means we're kind of ignoring some finite number of terms at the beginning of the sequence. So if we're that far out in the sequence, a sub n plus 1, remember, according to our recursive formula, that's x over n plus 1 times a sub n. We can make this bigger if we replace the numerator with a value that is larger. And what's larger than x? Well, n plus 1 is larger than x if we're far enough out in the sequence. And that gives us n plus 1 over n plus 1 times a sub n. But n plus 1 over n plus 1 is 1. So this is a sub n. Right. So what we see now is that if we are far enough out in the sequence, so eventually, a sub n plus 1 is less than a sub n. So a sub n plus 1 is less than a sub n. So our sequence is eventually decreasing. Okay. On the other hand, remember a sub n is x to the n over n factorial, and x is positive, so the nth term, x to the n over n factorial, is clearly greater than or equal to 0, right? This is a positive number divided by a positive number, so it's positive. So our sequence is also bounded below. Okay, so now we have a sequence that is eventually decreasing, and it's also bounded below. And that means that our sequence converges, right, by that theorem. Okay. Knowing that the sequence converges is really convenient, right? Because it gives us, that means we know ahead of time that the limit as n goes to infinity of a sub n is equal to some number, right? We don't know what number yet, but we know it's equal to some number. And just knowing that it's equal to some finite number is often very important because it lets you use all the limit laws. So let's write out our recursive formula again. So a sub n plus 1 is equal to x over n plus 1 times a sub n, right? We know that the series converges. Now we have to answer the question, to what? So write out our recursive formula, and what we can do is take the limit on both sides as n goes to infinity, because that's what we need to compute. So on the left, we get the limit as n goes to infinity of a sub n plus 1. On the right, we get the limit as n goes to infinity of x over n plus 1 times a sub n. Now this limit on the left, right, a sub n plus 1, this is the same sequence as a sub n. It's missing the first term. But what matters for the limit is what happens in the long run, so the first term doesn't matter. So this limit has to be the same as the limit as n goes to infinity of a sub n, and that's what we called L. Okay. Now on the right-hand side, what we would like to do is split this limit up at that product. But remember, we can only split that limit up at that product if we already know that the limit as n goes to infinity of a sub n exists. But we do know it exists because we know this sequence converges. So to do this, to split this limit up into two limits, a product of two limits, we have to know in advance that this limit exists, which we do know. It does exist. It's L. Okay. So now we have L equals the limit as n goes to infinity of x over n plus 1 times L. All right. But this limit of x over n plus 1 as n goes to infinity, well, this is 0 because x is a fixed value and n plus 1 is flying off to infinity. So this is 0 times L, and that means L is 0. Okay. So this is sort of a more precise way of understanding why the limit is 0 than some other tricks. It is a little more involved, but you can see how it's very this trick that we used of using a recursive formula and then already knowing that the series sequence converges and so the value L exists. You can see how just knowing that this limit exists, even if you don't know what it is, knowing that it exists can be a very useful fact. For recursive formulas, it lets you pull this kind of limit law trick to figure out what the value or what the limit of the sequence is.